How old is the Earth? Does time extend back before the Earth was formed? Has time always existed? Not so long ago, Bishop Ussher, an English clergyman, thought that he had determined on the basis of biblical data that the Earth is about 6,000 years old. However, when we look at the Earth on the basis of knowledge we have gained since then, we can readily believe that it is much older than that. It's not hard to imagine, for instance, that it has taken a very long time for the Colorado River to cut a path in the Earth a mile deep. And here on the top of a mountain, we find rock containing the fossil of an ancient sea creature. How many years has it taken for the Earth to change so much that an ocean floor has become a mountaintop? How many years? Thousands? Millions? Billions? In order to find out, we are going to have to measure the extremely long intervals of time over which these events took place. Now, when we want to measure time, we usually think of a clock. A clock is a mechanism that ticks at a known rate. With ordinary clocks like these, the time interval between ticks of a given clock is always the same. When we use a clock, we compare the time interval we want to measure with the number of times the clock is ticked. In this film, we will investigate clocks for measuring long intervals of time. Some of these clocks tick regularly, and others, oddly enough, tick irregularly. We use a clock which ticks slowly and regularly to measure the age of a man, for instance. The clock we use is the movement of the Earth around the sun. Every time it completes one revolution, we count one, and we call that tick a year. Now, this clock doesn't record the number of ticks it has counted. Men must keep records of the number of ticks it has made. In other words, the written record, written on paper or carved on stone, is an essential part of this clock. By keeping track of the yearly ticks of the Earth's movement around the sun, we are able to measure time intervals of hundreds and thousands of years dating back from now. For instance, we know that the Earth has gone around the sun about 6,000 times since the first pharaoh ruled in Egypt. But further back than that, we get lost. People didn't keep records. How can we measure intervals of time longer than 6,000 years if no one was watching the clock? In order to measure time intervals that are longer than the course of human history, we need a clock that records its own ticks. Here is a clock that records its ticks. Each ring in the cross-section of a tree trunk indicates a year of growth. This clock ticks off the years and keeps its own record of the number of ticks it has made. But even though this tree is one of the oldest living things, the time interval of its life is only about 3,000 years. Since we want to measure longer time intervals than that, we need a clock that ticks over longer periods of time, but, like the tree, counts its own ticks. Here is something that resembles the cross-section of a tree trunk. Over a long period of time, layer after layer of matter has been laid down one on top of the other. Is there a clock we can read here? Is there something we can measure? Was a new layer formed every year? No. Yet there are things here that can be measured. 100 years ago, the great geologist, Sir Charles Lyell, measuring time by sedimentary layers, estimated the interval of time since the age of the reptiles at 250 million years. He recognized that his estimate was rough,
but at least he had made a measurement of long time which was based upon scientific observation. Scientific observation has brought about the discovery of another type of clock ticking away inside the Earth. This clock is perhaps the most remarkable of all. It ticks irregularly, but when averaged over long periods of time, it ticks with great accuracy. Also, it counts the number of ticks it has made, and it records them in such a way that they can be read. This clock enables us to measure time intervals as long as the lifetime of the Earth. The clock is radioactivity.
This material is pitchblende, which is a natural uranium oxide. Uranium is one of several radioactive elements which are found in rocks and minerals. We can demonstrate that it is radioactive by placing it in this counter. Like most elements, uranium consists of a mixture of isotopes. Isotopes are atoms which have essentially identical chemical behavior, but with different masses. The most abundant uranium isotope has a mass slightly less than 238 times that of hydrogen, and we use this symbol to indicate that we are speaking of this particular isotope of uranium. About 99.3% of natural uranium consists of this isotope. A second uranium isotope is uranium-235. Natural uranium consists of about 0.7% of this isotope. Now, both of these isotopes of uranium are unstable. That is, they are radioactive. Ever so often, an atom of uranium-238 changes into the atom of another radioactive element. This new atom changes into the atom of a third radioactive element, which in turn changes into another, and so forth. Such a sequence of radioactive atoms is called a decay chain. Now, not all radioactive atoms are members of a decay chain, but it has been shown that uranium-238 is the first atom of a decay chain, which ends with the stable product lead-206. It's also been determined that uranium-235 is the first atom of another decay chain, which ends with the stable atom lead-207. Another isotope of lead. Now, the rate at which the average uranium-238 atom decays into lead-206 is remarkably constant. No matter how the uranium-238 is combined chemically, no matter if it is dissolved in acid or subjected to high temperatures or enormous pressures, the uranium-238 still goes on decaying without variation at its own unchanging rate. This is equally true, of course, for uranium-235. Now, here we potentially have two excellent clocks for measuring long intervals of time. Clocks which tick at an irregular rate, but when averaged over a large number of ticks, they're extremely accurate. They are not disturbed by changes in temperature and pressure, and under the proper conditions, they record their own ticks. The record they make is the number of lead atoms produced. Let this block represent a sample of pure uranium-238. There's no uranium-235 present, and more importantly, there's no lead of any kind. Further, let's assume that this block will remain a closed system. That is, nothing will enter or leave the block from now on. Now, since we know that uranium-238 decays to produce lead-206, we can expect that in the future there will come a time when half of this block will have decayed into lead-206. At that time, the ratio of the amount of lead to the amount of uranium will be 1/2 over 1/2, which equals 1. We can plot this information on a graph. We'll call the time interval t, and at the time t, we have a lead-to-uranium ratio of 1. The remaining uranium-238 will go on decaying, and it will be found that after a second time interval equal to t, half the remaining uranium-238 will have decayed, leaving 1/4 of the original amount of uranium-238 together with 3/4 lead-206. This is a lead to uranium ratio of 3/4 over 1/4, which equals 3. So we plot at time 2t a lead to uranium ratio of 3. After a third time interval t, half the remaining uranium-238 will have decayed. And we can plot at time 3t a lead to uranium ratio of 7/8 over 1/8, or 7. As you may have guessed by now, the time interval t is called the half-life of the radioactive material. The half-life is simply the time interval required for half of any amount of radioactive material to decay. In the case of uranium-238, the half-life is about 4.5 times 10 to the 9th years. If a smooth curve is drawn through the points we have plotted, we can determine the lead to uranium ratio at any time along the curve. Actually, it's possible to derive the equation for this curve. We can also plot the curve for the lead-207 uranium-235 clock. This curve is different because the half-life of uranium-235 is shorter than that of uranium-238, namely 7/10 times 10 to the 9th years. Now let's reverse the process. Suppose that in a rock such as this, there is a particular mineral in which the lead-uranium clocks are running. By this we mean that uranium-238 and uranium-235 are inside the mineral, decaying into lead-206 and lead-207. Now we have just established a relationship between the lead to uranium ratio of these two clocks and the length of time they have been running. So you see, if we can determine the lead-206 to uranium-238 ratio, or the lead-207 to uranium-235 ratio, then we can determine the length of time the clock has been running inside the mineral, and therefore the age of the rock. To determine these ratios, we need an atom sorter. That is, an instrument with which we can determine the relative number of atoms of the isotopes of lead and uranium in the rock. We have such an instrument. As a matter of fact, without such an atom sorter, we would not be able to measure long times in this fashion. A particular mineral which is useful for measuring long time by the lead-uranium clocks is called zircon. Zircons are chemically stable, and therefore, like our model, tend to remain closed systems. That is, almost nothing enters or leaves them. Also, when they were made, zircons contained very little lead. Therefore, any lead we find in them today is almost entirely the product of radioactive decay. Zircons are found in several types of rock.
This is a ledge of granite in a western mountain range. How long ago in the history of the Earth were the rocks of these mountains formed? The granite is composed of crystals formed when hot liquid rock cooled within the Earth's crust. Fortunately, much of the tiny amount of uranium in this rock went into minute crystals of zircon grown at the same time. If we can determine the age of the uranium clock at work in these zircon crystals, we can learn how old the granite is. First, we must process the rock to extract the small amount of zircon contained within it. The first step in this process is a delicate one. Now machines take over. The small bits of rock are ground to powder. Then the powder is sorted through sieves according to particle size. This machine separates the powdered minerals magnetically. The separation of the sample is continued with the use of a special heavy liquid, which weighs 3 times as much as an equal volume of water. When the powder is mixed with the liquid, the lower density mineral particles float, and the higher density minerals sink. Zircon is heavier than most minerals, and will be concentrated at the bottom of the flask. This device further sorts the particles by delicately distinguishing between their characteristic magnetic properties. Zircon is less magnetic than most minerals. Now the particles are finely sorted under a microscope. Purity of the zircon sample is necessary for successful reading of the clocks of radioactivity. We have separated less than a fraction of an ounce of zircon from 50 pounds of granite. We can now examine the uranium-lead clocks working inside the zircons. To do this, the zircons must be broken down chemically to extract the uranium and lead.
The chemical breakdown takes place in this specially designed lead-free laboratory. The quantities of uranium and lead which we must isolate are minute. It is important that the laboratory in which we read our radioactive clock be entirely lead-free and uranium-free, except for the samples we bring in. We don't want to confuse the lead and uranium in our clocks with any not belonging to the sample we are investigating. When the zircons are first brought into the lead-free laboratory, they are washed in a dilute acid to remove any lead contamination which they may have picked up previously. Now the zircons are dissolved in molten borax. After the sample is cooled, it is dissolved in acid. The uranium and lead are separated individually by special chemical solvents with unusual affinities for these elements. Hydrogen sulfide is bubbled through a solution containing the lead. A precipitate of lead sulfide is obtained. The precipitate, weighing 5 to 10 millionths of a gram, is placed on this wire filament. The uranium is concentrated in a solution which is placed upon another wire filament.
This instrument is our atom sorter. It's called a mass spectrometer. By placing the wire filaments loaded with the samples of lead and uranium inside it one at a time, we can determine from this record of the operation of the mass spectrometer the amounts of the various isotopes of lead and the amount of uranium contained in the sample. We calculate in the sample we have just analyzed a lead-206 uranium-238 ratio of 0.361. This ratio of 0.361, or about 4/10, corresponds to an age of about 2 times 10 to the 9th years. We calculate the lead-207 uranium-235 ratio to be 6. And this corresponds also to an age of about 2 times 10 to the 9th years. Since the two clocks of radioactivity agree as to the age of the sample, we have a high degree of confidence in the result. The sample is about 2 times 10 to the 9th, or 2 billion years old. Of course, we actually use the equations of the curves to get the precise ages.
With a good deal of accuracy, we have read two clocks, each of which ticks slowly enough and long enough to measure a time interval of 2 billion years. We use these clocks and others to date rocks and rock formations of many kinds throughout the world. How can we use these clocks to measure the age of the Earth? The oldest rock in the world yet measured by radioactivity is calculated to be about 3.2 times 10 to the 9th, or 3.2 billion years old. Since this rock was found in the Earth, we can say that the Earth is at least 3.2 billion years old. Thus, we have a minimum limit for the age of the Earth.
Now, can we find some indication for a maximum limit for the age of the Earth? It so happens that we can. By making special calculations on the relative abundances of U-235 and U-238, which were present when the elements were formed, and comparing that ratio with their present relative abundances, we can arrive at an outside limit of the age of the Earth of 10 times 10 to the 9th years, or 10 billion years. We can say then that the age of the Earth lies between 3.2 times 10 to the 9th years, the age of the oldest known rock, and 10 times 10 to the 9th years. We could be much more definite about the date if we knew what the isotopic composition of lead was when the Earth was formed. We could then calculate how long it would have taken for the original lead to have been transformed by the decay of uranium and thorium into modern lead. But unfortunately, when the Earth was formed, no one was around to measure the isotopic composition of lead. Can we measure it now? There is a theory that some meteorites, which come from outside the Earth, contain lead which today has the same isotopic composition as the lead that existed when the Earth was formed. This lead has been isolated from several meteorites and measured on a mass spectrometer.
Starting with lead of this isotopic composition, it is possible to calculate how long it has taken the decaying uranium and thorium to change the isotopic composition of the Earth's original lead, such as that found in this meteorite, to that which we find in the oceans and rocks today. The result of this calculation is 4.5 times 10 to the 9th years. And so we say that the time interval since the formation of meteorites and the Earth is 4.5 times 10 to the 9th, or 4.5 billion years. We have actually been able to obtain the same number using several other radioactive clocks on meteorites, so we are quite confident in the result. How about still longer intervals of time? How about the age of the elements from which the Earth was formed? Here we have a figure which is more than a guess, about 6 billion years. How about the age of the universe? No figure yet. Indeed, it may not even have an age. What about the nature of time? We know that we can measure time from very short intervals or short ticks to the slow ticks of billions of years. But we are not as expert when it comes to explaining just what time is. Like many concepts which seem commonplace and simple, the concept of time is both subtle and complex. Indeed, we have a great deal to learn about the nature of time.